Silicon debugging. Silicon debugging starts with the arrival of the design prototype and can continue well after a product has gone into production. It is the most exciting and challenging stage of the integrated circuit development process. This class gives an overview of silicon debugging and describes tools and methods used during the debugging process. Silicon debugging. The purpose of debugging is to identify and resolve any problems that exist in an integrated circuit to ensure that it operates correctly for customers over the specification range. The debug process can easily make the difference between success and failure of a design. The term bug has been used for over a century to describe design problems. There are three categories of bugs: functional, electrical, and manufacturing or yield. Functional bugs, also called logic bugs, are where the logic of a design is improperly implemented. Electrical bugs are where the functional behavior of the circuit is correct, but it fails to operate correctly in some part of the specified operating region, that is, at some voltage, temperature, or frequency. Manufacturing or yield bugs occur when a circuit is sensitive to some variable in the manufacturing process and changes its operation as a result of manufacturing variations. For example, an analog circuit's operation may be sensitive to the gate length used for a transistor and may fail due to the manufacturing variations between different dies. The goal of the debug is to find all bugs and eliminate them through design changes or other means before selling the device to a customer. This class briefly describes the process, design features, tools, and methods used to accomplish this goal. The debugging process. To start the debugging process, we need a detailed plan. This detailed plan must characterize and also must be validating both the functional and electrical properties of a design. When the design becomes complex, the debugging process also becomes complex. There are five major steps in debugging a particular failure. 1. Controlling the failure. Controlling the failure means we have to determine the sensitivity of the failure through experimentation. For example, if it is a functional bug, this must involve experimenting the sensitivity of the failure to different operators or different test vectors. If it is an electrical failure, this involves determining the sensitivity of the failure to environmental parameters like voltage, frequency, temperature, and process. Once the sensitivity of the failure are understood and a solid failure is obtained, the work begins on the isolation of the failure. This involves determining when the failure occurs and where in the design the failure occurs. These first two steps typically dominate the effort spent during the debug process for a bug. Once the root cause of the failure has been established, the final step in the debug process is to expand the failure. This has two components. First, we need to determine all the worst case conditions which we use to test the failure, and this should be this should be such that it can be used for future testing of the failure. The second is to ensure that there are no other similar types of failure in the design that might be the result of any kind of inadequacies in the design methodology used for testing that failure. After completing the debug process, a fix may or may not be developed d- depending upon the severity of the problem and its impact on the product. Depending on the product type and complexity of the design, this may take anywhere from 1 to 10 or more design revisions and 6 months to 2 years of work to complete the debug process to enable the shipment of the final product to the customer. Design for debug or DFD. Design for debug means that implementation of or adding of certain features into the design such that it aids the debugging process. Pre-silicon design for debugging. Our aim is to design such that it can be debugged. We are going to analyze some techniques for pre-silicon design for debugging. It is essential during the debugging process to be able to pinpoint both when and where a failure is occurring. This is enabled through DFT features which captures and assess the internal state of a device and manipulate this internal state in a very controlled manner. Enabling capture of such information requires the addition of some triggering circuitry to detect particular conditions during debug. Some techniques are scan-based techniques. The scan-based technique was taught when we took the design for testing earlier. Scan is typically implemented by connecting all the storage elements in a design, such as latches or flip-flops, together in a serial shift register, in addition to their normal parallel connection to the digital logic. This allows the data contained within the storage elements such as flip-flops to be serially shifted out by clocking them with some special serial shift clock. Thus, we can analyze the internal storage elements. We will be able to analyze the internal state of the storage elements, and we can manipulate these states using some buses connected to the shift registers. Next technique is the ability to manipulate the clocks used within a design. The ability to manipulate the clocks used within a design is also very important aid to debug. With the ability to move edges of the clocks within the device, again using some internal triggering circuits, it is possible to find the timing problems on signals and thus identify temporarily or when a failure is occurring. This is also known as finding the critical clock of the failure. Next method is using process variation monitor. Process variation monitors are identical circuits which are placed throughout a design which can be used to evaluate localized process effects. Typically, such circuits are ring oscillators which are configured to be sensitive to various electrical process parameters. Example, gate length, width, leakage, etc. Next technique is usage of power droop detection circuits. Power droop detection circuits may be distributed in a similar fashion around a die to allow evaluation of power supply disturbances. This can also be helpful in spatially locating places within a die where circuit might be failing. Next is the ability to inject artificial error condition or anomalous events into the hardware of the device to see how it responds. Next is post-silicon tools and methods. So now we know when the failure occur and where the failure occur through the pre-silicon design for debugging. So what is in essence the pre-silicon design for debugging is used for isolating the failure. That is the second major step in debugging. So the next step is determining the root cause of the failure. This is done by using the post-silicon tools and method. This is usually essential to validate that the failure is completely understood and sometimes to also check out a possible fix before actually implementing it within the design. The ability to check out a fix before committing it to silicon is critically important as revising silicon can be very expensive and time consuming, which can affect overall product schedule adversely. There are a number of tools which can be used to probe actual signals on a device to verify the root cause of a failure. One of the oldest is actual mechanical probing, where a very small mechanical probe is used to measure a signal on the device. This is very time consuming and error prone activity due to the incredibly small dimensions involved in today's devices. As a result, more sophisticated optical probing methods have become the standard for evaluating signals. This allows the backside of the device to be probed after appropriate processing using optical methods. This method takes advantage of the fact that silicon is transparent to infrared light and they are either active or passive. Another method is laser voltage probing. An infrared laser beam is applied to the backside of the device and eliminates diffusion of transistor. By observing the reflected laser light from the diffusion of the transistor, it is possible to determine when voltage transitions occur on a given node. This tool can provide oscilloscope-like traces of individual signals relative to each other, which is obviously extremely useful in debugging timing-related failures. Another technique is emission microscopy. Here, it makes use of the fact that the CMOS transistors in saturation emit infrared photons. Through use of a photodetector, it is possible to assemble the photon counts over an integration period to locate which devices are in saturation. Usually, devices which are either switching or are defective. So let's revise the debugging process. What is debugging process? The purpose of the debugging is to identify and resolve any problems that exist in IC, and we must ensure that the IC is working correctly before it reaches the customer. That is the debugging process. The debugging process, as we learned, comprises majorly 5 steps. Controlling the failure. Controlling the failure involves determining the sensitivity of the failure using experimentation. Next step is isolating the failure. Isolation of the failure means to identify when and where the failure is occurring. This is done by designing for debugging. That is, designing such that the circuit can be debugged. For isolating the failure, we use pre-silicon designed for debugging. Different techniques used for pre-silicon design for debugging are, as we saw earlier, scan based techniques, manipulating the clocks used within the design, using process variation monitors, using power droop detection circuits, ability to inject artificial error conditions or anomalous events into the hardware of the device and see how it responds. Next step is finding the root cause of the failure. This is done through post silicon tools and methods such as mechanical probing, laser voltage probing, emission microscopy, optical probing methods. Next one was expanding the failure. Expanding the failure means we must find all the worst case conditions when a failure occurs, and we must be able to do future tests for the failure. Next step is fixing the failure. Fixing the failure can be done through focused ion beam edit or FIB. FIB edit is a form of silicon microsurgery where an ion beam is used to dig through a die to allow metal connection to be cut or made to individual transistors or to trim existing transistor. A FIB edit can be tremendously useful in correcting a functional or electrical bug and allowing it to be validated prior to fixing it. For example, a functional bug can often be corrected by rewiring the signals and using some spare gates inside the ICs, which are scattered throughout the design for enabling such FIB edits. So, this is the overall debugging process.